So we're going to examine parallel and perpendicular a little bit more closely and then start decomposing vectors. So we said that if the dot product of the two vectors was 0, let's say we've got vector v and w, and we want to find the angle between. So cosine of theta would be equal to the dot product of v dot w over the product of the magnitudes. And we said in the last video that really what happens to theta depends on what's going on in that numerator with that dot product. We said if that dot product was positive, then we would get an acute angle, something between 0 and 90 degrees. If the dot product's negative, we would get something between 90 and 180 degrees. And if that dot product is 0, then we're going to end up with perpendicular vectors. And orthogonal is just another way to think about perpendicular. Talk about perpendicular when we're talking about two-dimensional space. If we're talking about things in 3D or beyond, then we talk about things being orthogonal. But what does it mean to be parallel in this kind of world? Well, two vectors are parallel if we can write one as a scalar multiple of the other. When we're talking about non-zero scalars. So for instance, let's say we have vectors u is 1, 2, and then vector v is 2, 4. We would say these are parallel because vector v can be written as 2 times vector u. Okay, or we could actually think about u as 1/2 of v. Okay, so either way, you see that parallel relationship. Okay, so all that means is that they're going in the same direction. One's going to live on top of the other. The only difference is one's going to be longer than the other. So what's interesting about the 0 vector is actually parallel and perpendicular, or say orthogonal, to every vector. So that's a very special vector. All right, so now let's talk about decomposing. So with decompositions, what we want to do is we want to take one vector and we want to project it onto another vector. So we're going to have v and w. We're going to deal with v and w here. Two non-zero vectors, and we're going to project v onto w. When you hear the word projection, I want you to think about a shadow. Okay, so if I have a flashlight over that vector, and I'm doing this at a 90-degree angle, if I have a flashlight on that vector, it's going to project a shadow. That shadow is the projection that we're talking about, and that's going to produce v1. Now notice this is going to be a scalar multiple of w, and that scalar value is going to be the dot product of v and w over the magnitude squared of w. To find the other vector, because we're decomposing in the two vectors, we're going to take v2, that's our second vector, and take the original v and subtract that scalar multiple v1 that we just found. So I want to do a really simple example here of this. So suppose vector v is the vector 3, 4, and vector w is the vector 7, 0. So I'm going to draw a picture of what's going on. So here's the vector 3, 4. 7, 0. And what we're going to do is we're going to find that projection first. When we think about what I was talking about with the flashlight, you want that flashlight to be orthogonal to W. because that's what we're projecting on. We're projecting on the W. So if I'm thinking about a flashlight, here's my little flashlight here, okay? And it's shining. I have to be orthogonal, which means perpendicular to W. So I've got my flashlight perpendicular to W. That shadow is what we're looking at. So you see how that shadow is going to be this piece right in here. Well, we're going to find that vector. Okay, this one's really easy to kind of see what's going on. And I did that on purpose, and we'll do a harder one in just a minute. So to find V1, it's going to be V dot W over the magnitude of W squared. So if I dot V with W, I'm going to have 21 plus 0 over the magnitude squared. The magnitude of W would be 7 squared plus 0 squared. And I'm going to multiply that by vector W. I left that out there. Vector W is 7, 0. So let's clean this expression up. I have 21 over 49. And that squared and that square root cancel out. So I just have 49 in the bottom. 7, 0. 21 divided by 49 reduces to 3 over 7. So there's my scalar value. You can see it's a scalar multiple. And if I multiply that back through, I'm going to get 3, 0. So this is going to be parallel to W. V2 is going to be perpendicular to W. So V minus V1. So I'm going to take V, 3, 4, and I'm going to subtract V1, which is 7, 0. Oh, hold on a minute. I'm looking at the wrong thing. Sorry. I've got V, and I'm going to subtract V1, which is 3, 0. So 3 minus 3 is going to be 0. 4 minus 0 is going to be 4. So there's my vector. This guy is going to be perpendicular or orthogonal to W and V1. So let's graph what we have. So V1 is going to be the vector 3, 0. So there's my V1. And V2 is going to be 0, 4. And you can see how V1 is definitely parallel to W, and V2 is definitely perpendicular to both V1 and W. So that's what it means to decompose. So let's do another example. And this is where you may want to pause the video. So I'll write my example down here. Let's say how we have vector V as the vector negative 3i plus 2j. So I'm going to use ij notation. But it works the same way. W is 2i plus j. And you may want to pause the video, try it, and then come back and check your answer. So to find V1, it's going to be V dot W over the magnitude of W squared. So V dot W is going to be negative 6 plus 2 over the magnitude squared of W. And then we're going to multiply that by W. Don't forget that W there, which is going to be 2, 1. So let's simplify what we have. We're going to have a negative 4 in the numerator. This is going to be a 5 in the denominator after I square that square root times 2, 1. And we're going to end up with negative 8 over 5, negative 4 over 5. V2 is V minus V1. So I'm going to take negative 3, 2. Now I'm going to subtract. negative 8 over 5, negative 4 over 5. Negative 7 over 5 is my first component. -14 over 5 is my second component. So this guy is parallel. V1 is parallel to W. V2 is orthogonal to W. So I've graphed everything in GeoGebra. GeoGebra is another online grapher. It's easier to do vectors in GeoGebra than it is Desmos. That's why I chose that. So I've got vector V and I've got vector W graphed. So here's a vector V and here's a vector W. Now, we were talking about that flashlight, right? We want a flashlight over V so that is projecting on the W, but we've got to be orthogonal to W. So my flashlight is going to be somewhere up here. Oops. Somewhere up here, and it's going to be shining. And you can see if it's shining orthogonal to W, it's going to project something somewhere along here. And that's what vector A is. Vector A is going to be parallel to W. Now, in this case, it's parallel in the opposite direction, which is perfectly fine. The definition of parallel means it's a scalar multiple of W. So there's my parallel vector, and then my B vector has to be orthogonal to A, and you can see how it's going to be orthogonal to A. And then by default, it's going to be orthogonal to B, because A and W are, it's going to be orthogonal to W also, because A and W are just scalar multiples of each other. So that's what we found. Vector A is going to be parallel to W, in this case in the opposite direction. Vector B is perpendicular to W.